A fully loaded freight train racing at 70 miles per hour holds more energy than a speeding bullet. Over 1 billion joules, barreling across the rails with the weight of 500 elephants. But when it's time to stop, friction alone is not enough. Stopping a 2,500-ton locomotive takes more than just steel on steel, and sometimes even a mile is not enough runway. How do engineers keep disaster at bay when physics seems stacked against them? The answer reveals a hidden battle at the heart of every high-speed journey. At 70 miles per hour, a 2,500-ton freight train carries kinetic energy approaching 1.1 billion joules. That is the same punch as detonating 260 kilograms of TNT. Every second, the train's mass and speed multiply into a force that dwarfs anything on the highway. But the challenge is not just about raw energy. It is about how much of that energy can actually be controlled by the steel wheels gripping the steel rails. Each axle beneath a heavy freight car bears around 22 tons. Multiply that by 100 cars and you have nearly 400 axles, each responsible for turning momentum into manageable friction. But the grip between wheel and rail, what engineers call adhesion, has a hard ceiling. Even under ideal conditions, only 20 to 30% of the weight pressing down on each wheel can be turned into usable braking force before the wheels begin to slide. That is the limit imposed by physics, steel on steel, with no room for error. Imagine a locomotive engineer pulling the brake handle. The system can only ask so much of each wheel before the iron law of adhesion pushes back. Exceed that threshold, and the wheels lose their hold, spinning or sliding uselessly on the rail. The braking force available is locked to the weight on each axle and the quality of contact. No matter how desperate the need to stop, the laws of motion will not bend. This means that stopping a train is not just about adding more brakes or pushing harder. It is a careful negotiation with physical limits. The entire braking system, from the engineer's hand to the last car, is designed around the fact that there is only so much grip available. The numbers are unforgiving. With a full emergency application, the maximum deceleration achievable is just a fraction of what a car can manage, typically about 0.3 meters per second squared. The scale of energy and the narrow window for traction define every decision an engineer makes when slowing a mile-long, 2,500-ton train barreling down the track. From the moment a freight train's brakes are applied, the numbers start working against it. With a maximum deceleration of 0.3 meters per second squared, a 2,500-ton train running at 70 miles per hour will not stop in a matter of seconds, or even in the distance you might expect from a highway vehicle. The reality is far more daunting. It takes more than a mile of track, sometimes closer to 1.5 miles, for the train to come to a complete halt under full emergency braking. This immense stopping distance is not a product of caution or conservative engineering. It is the direct result of physics at work. The train's mass and speed create momentum that cannot be quickly erased, no matter how hard the brakes are applied. Even with every axle working in concert, the available friction between wheel and rail can only pull the train down from speed at a measured, relentless pace. The steel wheels and rails, designed for efficiency and durability, offer only a thin margin for grip. If the brakes demand more than that margin allows, the wheels will slide, and the train may take even longer to stop. For an engineer in the cab, this means every decision carries weight long before the train reaches a crossing, a signal, or a curve. A car traveling at highway speed can stop in a few hundred feet. A fully loaded freight train, by contrast, will roll on for thousands of feet, well over 20 times the length of a football field before coming to rest. There is no room for last-minute reactions. Every planned stop, every reduction in speed, must be anticipated far in advance. This is why railroad operations hinge on careful calculation and timing. The sheer scale of the train's momentum, combined with the limits of adhesion and deceleration, transforms the simple act of stopping into a complex, coordinated process. The challenge is not just to slow the train, but to do so safely, predictably, and within the physical boundaries set by the rails themselves. The next step is to understand how mechanical systems have evolved to meet these demands, blending technology and engineering to manage forces that stretch for over a mile. Inside the locomotive, traction motors do more than just drive the train forward. They become generators when it is time to slow down. When the engineer moves the dynamic brake handle, the motors switch roles. Instead of drawing power, they start converting the train's momentum directly into electricity. The faster the train moves, the more electricity these motors can produce. For a modern diesel-electric such as an SD70AC or GE ES44AC, that means each locomotive can handle between 2 and 4 megawatts of dynamic braking power, enough to power a small town, but only for the seconds it takes to bring the train under control. But this electricity has to go somewhere. In North American freight service, it is sent to massive resistor grids mounted in the locomotive roof. These grids are made of stainless steel or nichrome ribbons, wound tightly and set on ceramic insulators. As the current flows through, the grids heat up, sometimes reaching 600 to 800 degrees Celsius. Powerful fans kick on, pulling thousands of cubic feet of air each minute to keep the system from overheating. In heavy mountain territory, engineers can feel the heat radiating through the car body, and on night runs, the grids sometimes glow a faint cherry red. A systems engineer explains that this process is a balancing act. The resistor grids are designed to handle peak loads, but if the train is descending a long grade, the grids can approach their thermal limits. The locomotive monitoring systems track grid temperature and current in real time, and they are ready to trip out if things get too hot. At high speeds, dynamic braking is at its strongest, but as the train slows below 10 miles per hour, the amount of energy the motors can convert drops sharply. That is why dynamic braking alone cannot bring a heavy train to a complete stop. Below this threshold, the system fades, and the engineer must rely on pneumatic air brakes to finish the job. This blend of electrical and pneumatic braking is what allows a 2,500-ton train to slow safely, even when gravity and momentum are working against it. Compressed air is the nervous system of a freight train. The brake pipe, running the entire length of the train, is charged to 90 pounds per square inch before departure. Every car, from the locomotive to the last, is connected by this pipe, and each car's brake system is built to sense even the smallest changes in pressure. When the engineer pulls the brake handle, a valve in the cab releases air from the brake pipe. This pressure drop travels down the line at the speed of sound in air, but the sheer length of a mile-long train means it can take up to 90 seconds for the signal to reach the last car. As the pressure falls, each car's control valve springs into action. The valve detects the drop, opens a reservoir, and sends air into the brake cylinder, forcing the brake shoes against the wheels. The harder the pressure drops, the more force is applied. For a full emergency stop, the system dumps the brake pipe to near zero, activating every brake on the train with maximum force. This design is fail-safe by nature. If a hose bursts or a coupling separates, the sudden loss of pressure triggers the brakes automatically. There is no need for human intervention. The train will stop itself. Conductors and brake technicians rely on this principle every day, knowing that the system's default is safety. But the process is not instant. The air signal must propagate, and delays can mean the front of the train is braking before the rear even senses the change. That is why engineers and conductors constantly monitor brake pipe pressure, using telemetry and end-of-train devices to watch for uneven responses or leaks. Any irregularity, a slow pressure drop, a lag in the rear car's response can hint at a leak or a stuck valve. Routine tests and inspections are built into every trip, ensuring that the entire chain, from the engineer's hand to the last car, responds as intended. In the world of heavy freight, the brake pipe is more than a pipe. It is the lifeline that keeps 2,500 tons under control. Every second in the locomotive cab, a stream of data flows across digital dashboards and analog gauges, turning raw physics into actionable information. The engineer's eyes move from the speedometer, ticking down from 70 miles per hour, to the brake pipe pressure gauge, which hovers near 90 psi before any brake application. Next to it, a dynamic brake notch indicator shows how much electrical braking force is being called up, measured in notches from 1 to 8, each representing a step in the system's power output. At full notch, the traction motors can absorb up to 4 megawatts per locomotive, their converted energy tracked by an ammeter climbing with every notch increase. The dashboard also displays the train's total tonnage, a figure that shapes every decision. For a 2,500-ton consist, the engineer knows that every side drop in brake pipe pressure triggers a proportional response from each car's brake cylinder. Real-time readouts show the pressure change propagating down the train, with end-of-train telemetry confirming when the last car's brakes have responded. On a mile-long train, this lag can stretch up to 90 seconds, an eternity at highway speed. Blending dynamic and air brakes is a process visible in the cab's data overlay. As dynamic brake effort peaks, the engineer begins to feather in air, watching the brake pipe pressure fall and the brake cylinder pressure rise. Too much, too soon, and the wheels risk sliding. Too little and the train might not slow in time. The feedback loop is constant: speed, brake effort, pressure, tonnage, and adhesion, each variable shifting second by second. This telemetry is more than numbers. It is a living map of the train's response, giving the crew the information they need to manage forces that stretch for over a mile. Every indicator becomes a decision point, blending technology with human judgment to keep 2,500 tons safely under control. A freight train's ability to stop safely at high speed depends on more than physics and machinery. It relies on a strict culture of planning, testing, and verification. Every run begins with a detailed braking curve, calculated by the operations planner. This curve is not just a line on a screen, it is a living document shaped by the train's weight, length, speed, and the terrain ahead. Software factors in the steepness of grades, the condition of the rails, and the weather forecast. For a 2,500-ton train, the planner might flag a 1.5-mile stopping zone for a 70 miles per hour approach, adjusting for a 3% downgrade, or wet tracks that could cut adhesion in half. Before departure, a Federal Railroad Administration inspector walks the line, clipboard in hand, checking each car's brake system against a precise checklist. One key measurement is brake cylinder travel. If the piston moves less than 1.75 inches, or more than 2 inches, the car is sidelined for repair. The inspector listens for the hiss of air as the system charges, watches the gauge as pressure builds to 90 pounds per square inch, and times the release to ensure the brakes respond in under 20 seconds. Any leak, stuck valve, or lag in response can mean the difference between a controlled stop and a runaway. The checklist culture runs deep. Every car must pass a Class 1 brake test under federal rules. No exceptions. The inspector logs the results, noting which cars required adjustment or replacement of seals. If a single valve fails to move or a pressure drop lingers too long at the end of the train, the entire consist is held back. The planner, meanwhile, updates the braking curve to reflect any changes, recalculating safe speeds for each stretch of track. The process is relentless, repeated at every terminal and yard. It is not about bureaucracy. It is about ensuring that when the engineer makes the call to brake at 70 miles per hour, every component from the cab to the last car is ready to respond. Human decisions, guided by data and routine, form the final safeguard against disaster. Rain slicks the rails, snow clings to couplers, and summer heat softens the steel beneath a 2,500-ton freight train. Each of these conditions alters the delicate balance between wheel and rail, shrinking the margin for safe braking. On a wet track, adhesion can drop by half. A train that might stop in a mile on a dry day could need nearly 2 miles if the rails are icy or covered in leaves. Engineers adjust their braking curves with every weather report, knowing that a sudden storm or unexpected frost can turn a routine descent into a test of judgment. But the environment shapes more than just the day-to-day. It pushes the technology itself to evolve. In North America, dynamic braking remains the backbone for controlling speed on long grades, with resistor grids glowing red as they dump energy as heat. Elsewhere, the story is changing. European and Australian railways have adopted regenerative braking, sending electricity from braking trains back into the power grid. On some routes, this can recover up to 30% of the energy otherwise lost as heat, enough to power thousands of homes on a busy day. While North American freight trains still rely on resistor grids, the promise of energy recovery is drawing new interest, especially as hybrid locomotives and partial electrification projects gain traction. This drive for improvement has deep roots. In 1869, George Westinghouse patented the first automatic air brake, a system that used compressed air to apply brakes across every car at once. His invention transformed rail safety, replacing the chaos of handbrakes with a coordinated, fail-safe response. Archival accounts tell of early demonstrations where a split train, suddenly uncoupled at speed, stopped itself as air rushed from the ruptured pipe, proof that the system could save lives when everything else failed. Today, the spirit of Westinghouse's innovation endures. Railroads test new materials, smarter controls, and even artificial intelligence to predict and manage braking under changing conditions. Regenerative systems, advanced sensors, and distributed power units are all part of the ongoing effort to make stopping a 2,500-ton train at 70 miles per hour not just possible, but safer and more efficient with every passing year. Safety and efficiency remain the priorities. Every day, freight trains move nearly 1.7 billion tons of goods across the United States. Every journey depends on the precision of their braking systems. As rail networks expand and trains grow longer, safety hinges on engineers anticipating the unpredictable. The science behind stopping is not just physics, it is public trust. Because on the rails, every second counts. Share your thoughts on railway innovation below.